All right, here we go. The second part of geometric sequences. We've talked about initial values. We've talked about a common ratio and things I want you to pick up during this video. So first is how to represent the geometric sequence in a table. And hopefully you'll be able to see the value of doing that in transitioning from just a sequence of numbers in a straight line into a table. And if you're wondering what a table, it's going to be, some people like to call these things T-tables. We're going to be doing something like this. But we're going to translate from a sequence to a table. The second thing, and the most critical thing that we're going to be looking at here, is this idea called an explicit formula. And the explicit formula is going to be a very powerful tool that we're going to use that allows us to make jumps in our sequence, to make accurate predictions in our sequence, and so we'll get into those things as well. But again, the biggest takeaway here is going to be the explicit formula. But we're going to use the idea of a table to try and get us to that explicit formula. So if you recall, the last example that we looked at in our previous video was this sequence here. Okay, so given this sequence, we want to find the explicit formula. And again, from this sequence, we found last time that our common ratio, lowercase r, was 3. And our initial value, oops, didn't spell that right. Initial value was, in this case, the 3, where we started at. All right. So here's what we're going to do. We're going to take all of these numbers and we're going to transition them into a table. So every number you see in your sequence here, 3, 6, 12, 24, and so forth, these are called terms. So we're going to create a table and save yourself quite a bit of room here. So save yourself some space. So we're going to make a large table. This might go actually all the way across your line paper here. And I would hope you would write this down, because this is not going to be something that's going to stick in your brain after seeing it one time. It's going to take a little bit to get through this, but it's an effective way to come up with this, what we're going to call explicit formula. So over on the left here, we're going to write the term, and that's going to be like what term we're in our sequence. So we've got our first term, which is 3. So that you got your term, and then this is going to be kind of like our number in the sequence there. So our second term in the sequence is 6. Our third term in the sequence is 12. Our fourth term in the sequence is 24. And then our fifth term in the sequence is 48. Okay. And then we could go on. I mean, you could get your sixth term in there, and I'm hoping that you realize that our common ratio is 2, so our sixth term would simply just be taking the 48, multiplying it by 2 to get us 96. Alright, so I mean, that's cool. We got a table, but it doesn't tell us a whole lot about kind of the structure of our geometric sequence. It just gives us the numbers and what term we're on. So here's what I'd like you to do. This is where we're, might get a little wild here. It's okay in math to make things a little bit wild. So we'll turn to purple. Okay, now what we're going to do is we're going to kind of look at the math that's going on in these numbers in our sequence. So our first term is 3. Nothing too exciting on the first term. I mean, it's just 3. That's what it is. But then, to go from 3 to 6, we did something mathematically. Okay, we took the 3, we took the previous term, 3, and we just said, well, we multiply by 2, and that's what gives us the 6. So 3 times 2 is a 6. So hopefully you can see the connection there with those two. I mean, clearly 3 times 2 is 6. All right. Then, what we did is we took the 6, which we can say is 3 times 2, and you just rewrite that below it. 3 times 2, which is 6. And to get to 12, we simply just multiplied by 2 once again. So 3 times 2 times 2 gives us 12. All right, let's keep going with this idea. Whoops. Okay, so for 24, we took the previous term, which was 3 times 2 times 2. So when I say previous term, I'm taking this thing right here. Okay, and then to go to the next term, we just said times 2. And that gives us 24. Okay, and if you don't believe me, you can always check that. And then we could do that one more time. So we take the previous term, 3 times 2 times 2 times 2. And to go to our next term, we simply multiply it by 2 once again. And I hope you can see what we're kind of creating here. I mean, you can see this almost like we're building some steps here. So maybe that line doesn't necessarily justify what I'm saying, but we're kind of building these steps here, right, in our sequence. And we could do the 96 as well, but I hope you can see that this is getting pretty cumbersome. Because, well, what if, suppose that you wanted to really make things interesting and you wanted to jump out to the 10th term. And, the big question is going to be, all right, well, what is that 10th term? And one thing you could do is you could just sit there and multiply by 2 until you get up to 10. Or you could break out, the math over here, and you could have 3 times 2 times 2, but then you'd have to figure out how many 2's there are. So what we're going to do is we're going to extend this table one more length here. Okay, and we're going to break the math down and kind of create a structure that looks a little cleaner. All right. So again, we started with 3, nothing too exciting there. Okay. The next one, we had 3 times 2, and we only multiplied by 2 one time. So 3 times 2 there. Now I want you to think for a minute here. You may need to pause the video, but I want you to think, is there a way, or a shorter way, that you could write out something like 2 times 2, or 2 times 2 times 2, or 2 times 2 times 2 times 2? Think of a shorter way. Is there a shorter way to do that? So maybe pause the video for just a minute and see if you can come up with a way to do that. Alright, welcome back. Hope you paused it and thought of that. And hope you were thinking along the lines of exponents. So when you multiply by 2 once, that's 3 times 2 to the first. And then down here we have 3 times 2 to the second. 3 times 2 to the third. 3 times 2 to the fourth. And so on. And so these, I've got a lot of things highlighted here. My bad. So I hope you see that the 4 in this exponent is referring to the 4 2's here, multiplied together. The 3 in this exponent is the 3 2's multiplied together. Okay. So now, if we go down to this question that I asked earlier about the 10th term, I want you to think about what that's going to look like. Well, everything here has got a 3 times 2 in there. And if you notice, all of these exponents, 4 is 1 less than 5. 3 is 1 less than 4. 2 is 1 less than 3. So hopefully in this case you can see that the 10th term is just going to be 3 times 2 to the 9th power. Okay. And there we've got a structure. And so then you can take that and do all sorts of good things. We're just going to kind of wrap this up with a formula here. So now what we want to do is we want to throw a variable in there. Let's just say x. What if we're on term x? We didn't really know what term we were on. We just wanted to say, a variable x that will give us the value at any term. Well, in all of this stuff we have here on the right hand side, there is a common pattern. 3 times 2. Every one of them has that. Sorry, this 9 is bothering me. It looks really lousy. There we go. Okay, it's 3 times 2. And now, if we look at the exponent, well, we said the 9 is 1 less than the 10. The 4 is 1 less than the 5. So we want to figure out how are we going to be 1 less than x. Well, if you want to be 1 less than a number, you start with that number, x, and you just subtract 1. Because 9 is 10 subtract 1, 5, or excuse me, 4 is 5 subtract 1, and so forth. Okay. Sorry, this video is going a little bit longer than I would have liked, but I think we're getting into some good stuff here. We'll just wrap it up. So this thing right here is what we're going to call our explicit formula. So our explicit formula for this, we could write this as a function, would be the function, we'll just say f of x equals 3 times 2 to the x minus 1 power. And that'll give us any value in our sequence, or any term in our sequence that we want to, we just plug x in for that. So if you wanted, say, the 100th term, you would just plug in 100 to that formula. So you do 3 times 2 to the 100th, subtract 1 power. Don't try that in your calculator, it might blow up. No, that's probably just going to give you a memory overload error. So the explicit formula allows us to find any number or any term in our sequence without having to sit there and go times 2 times 2 times 2 using that common ratio over and over again. All right, so hopefully you're able to get an idea as to how to represent the sequence in a table and what I mean when I say an explicit formula.